All right. Moving on to our next story. Let's talk a little bit about the moon. Very, very uh cool video that I saw on Twitter the other day, and I thought I wanted to kind of talk about it and then also talk about the moon and this is going to be another edition of just how lucky we are to be alive on this planet. So, NASA Ames Research Center and Durham University put out this 3D model of a simulation of what happened when they believe that the moon impacted with our Earth. Now, obviously, it takes a lot of research in order to prove that this actually happened, but using computer models and using samples that they have collected both from moon and lunar missions, both manned and unmanned, they have put together all of this data into a massive computer, and it turned out a result in which they were able to provide a visual aspect of actually what happened and what we can think created our moon. So we can kind of see this right here. Let's take a look. A fresh take on the origin of Earth's moon. See that first crash right there? The the rippling. And they are saying that the moon most likely formed in just a matter of hours. And you can see the different, if we stop it right here, the different separations. So on the far left is Earth right there. In the middle is a bunch of matter that's ultimately going to get sucked back into the Earth itself. And then you'll see what happens to this far right outermost piece. Another crash back into the Earth. And then voila. So here we have a close up right here. And as you can see right here, I'll slow down the playback speed. We'll go at quarter speed right here. And you can see, let's go back a little bit. So you can kind of see right here the shifting and the pull right here. That looks almost like an egg when it's this close to the Earth because of the gravitational force of the Earth. You remember, talked about it before, but the core of the Earth is metal basically. And so it has very, very dense and a lot of mass, or it is very dense and it has a lot of mass. But so as the moon gets closer to Earth, it gets pulled into Earth, and you can see this almost spaghettification right here. There, it crashes into it, sends a shock wave throughout the entire Earth, breaks it apart, and it creates just this rippling effect on the planet, which is just absolutely phenomenal. I mean, look right here. I mean, that's just a crazy visual. Imagine being a observer to that. Three forms two different bodies right here. You can see the Earth is recovering, and in some aspect, it's still jiggling from that massive impact. Now let's go back to the normal speed right here. You can see it. And like I said earlier, far left, middle, far right. Watch what happens. That further piece out there is going to become what we now know as the moon. And that rest is going to be drawn back into the Earth and become a piece of the Earth. The gravity of the larger bodies propels the smaller body forward. And as you can see, boom, that gets sucked in. And then that far right piece now turns into an orbit around our planet. Simulation opens up new possibilities to the moon's evolution, not creation, but the evolution, and will help researchers better understand the intertwined history of Earth and the moon. because the moon is, believe it or not, pretty important. All right, moving on to our next story. If it'll let me switch it right here. All right, perfect. This is University of Chicago, an article about how the actual moon itself formed. You saw the video right there to kind of give a visual aspect, but now let's kind of talk about how it happened. It's to this point very widely believed that it was a collision from a foreign object that came and collided with a very early version of our planet. So, over 4.6 billion years ago, out of a mixture of dust and gas around the young sun, the Earth was formed. It grew larger thanks to countless collisions between dust particles, asteroids, and other growing planets, including one last giant impact that threw enough rock, gas, and dust into space to form the moon. Although the rocks that record the earliest parts of Earth's history have been destroyed or deformed over time by more than 4 billion years of geology, scientists can use modern rocks, moon samples, and meteorites to figure out when and how the Earth and moon formed and what they might once have looked like. So, big question is, how did it form? It was obviously, by most people's guess, it was a collision of some sort. The dust particles were brought together by the forces of drag to form clumps of rock that grew into what scientists called planetesimals, which are tens to hundreds of miles across, and then to Mars-sized protoplanets by colliding with each other. So Mars size, so fairly large planets. Mars is smaller than the Earth, but it still is a pretty big object. Earth grew to its final size through one last major collision with another Mars-sized object. This last collision, also known as the moon-forming impact, was so large that, in addition to adding lots of material to the Earth, there was enough energy to vaporize some of the rock and metal from both the proto-Earth and the impacting object. This vapor formed a disk around the Earth that eventually cooled and clumped together to become the moon. We know this thanks to the rigorous studies of meteorites and rock samples, including at the University of Chicago in the 20th and 21st century. Understanding how the Earth and moon formed is important for piecing together the history of the solar system and answering questions like how long planets take to form, what planets are made of, and what makes a planet sustainable for life, which is what I care about. I want to know what gives life. Now, they go on to talk about the early Earth forming. And now let's go on to the moon. Several different formation theories for the moon have been proposed by scientists. The story that is best supported by all the available data, however, is that the moon formed during a giant impact between the proto-Earth and another protoplanet roughly the size of Mars, sometimes called Theia. So, very early version of Earth was chilling out there, rotating in orbit around our sun. And due to the gravitational force of our home planet, Earth, it brought a foreign object, what they list here as a protoplanet, which basically just means a smaller planet that doesn't have like an atmosphere or anything. It's basically just a giant rock roaming throughout space. And then it got pulled into the gravity of Earth and ultimately crashed. And like we saw in the in that video, in that computer simulation, it not only did it just hit one time and then kind of just go, it continued to orbit around and continue to break off more and more and more. And then ultimately the Earth kind of got what it got. And then the moon was created as a little piece broken off from that in the orbit around our planet. In this theory, the moon formed from the impact debris, a mixture of molten rock and hot gas flung out into space by the impact, potentially forming a disk of material known as a lunar synestia. However, there are some other theories. there is a theory that the moon broke away from the Earth. So kind of the idea is that the Earth was just hanging out, and then due to a certain force or a certain action, a piece of the Earth broke off, and then that kind of shifted out into the orbit of where the moon is currently now. Another one is the moon formed elsewhere in the solar system and was captured by Earth's gravity. So in this case, there is no collision, which creates a breaking up of these two bodies where one body kind of sucks up most of the mass and then the other one just kind of goes out into a kind of close orbit and orbits around that thing. This is just a moon or something about the size of the moon is passing by, and as the Earth is going through its orbit, it catches just at the right time this moon in this, I guess, protoplanet, as we have been referring to it as. And then that is what, without any collision, without any real I guess injury or any effect on the Earth outside of just low gravitationally, then that would start to orbit. Now, okay, they do have some examples of I believe they have some examples of the kind of or wait, no. That's something else. I was going to say they have evidence of the moon particles from the collision here on Earth, but that is not possible because I mean, the reason why they do believe it was a collision is because if there wasn't, or if there was a collision, then it would have gotten so hot and so so destructive that there really wouldn't be any particles that we could see from something that happened billions of years ago in a fiery explosion and collision. And then the third alternate theory that they have listed here is that Earth and moon formed from the protoplanetary disk at the same time. So quick backstory, protoplanet disk is going to be when the sun was first forming and the gas that kind of started that early fusion around on the interior of the sun, which started the sun up and allowed for it to fuse hydrogen into helium and ultimately allowed for the sun to create. There was a giant gas cloud around it. And within that gas cloud was metals and different elements that would ultimately make up our planets that we have today. And so there was this kind of disk that would form around the sun, kind of like a pancake almost. And the reason for that is because the sun was turning. And due to the force of the turn, like if you take a pizza dough and you spin it around, it's not going to stay in a ball. It's going to kind of flatten out on a straight surface. Same thing happens with the sun or other stars that we observe elsewhere into our galaxy. And so kind of what this is pointing to is maybe during that period of where there's this layer, this pizza disk on the exterior of the sun that's orbiting around the sun, there were pockets there where we are fairly certain that the Earth formed via the protoplanetary disk and certain elements within it that make up the core of our Earth, those kind of joined in together. And then many other different factors, including meteors or asteroids or direct impacts with that young Earth planet, would ultimately add more mass, would add different elements to the crust of the Earth. And then over the course of billions of years, it would eventually become what we now know today, where we have an atmosphere, we have oceans, we have mountains, we have what we have today. But that started from a protoplanetary disk where you're going to have a lot of different elements kind of forming around the early sun. Now, next section is how do we know? How do we know that this particular theory of a collision, how do we know that that's the most likely one? What's the data? What's the science? Samples of rock from the moon brought to Earth by lunar meteorites and the Apollo moon landings can be used to understand the history of the moon and its relationship to the Earth through the chemistry of their minerals. Now, this would just be very awkward if they faked those moon landing missions, which you can debate whether or not that actually happened in terms of did the moon landing actually happen? I'm not going to tell you it did or it didn't. I would like to lean on the side of that it did because they have rocks from the moon and can analyze these things for yourself. Obviously not me or you, but people in labs have analyzed these things and they're like, yeah, that's the moon. That's not from here. But you have people like planetary scientist Nicholas Doufus and Professor Andy Davis in the Geophysical Sciences Department at the University of Chicago make precise measurements of lunar samples to determine exactly what they're made of and identify the chemical fingerprints of different geological processes like the melting and mixing of rocks and the evaporation of gases. The first big clue about where the moon came from comes from oxygen. Oxygen, like many other elements, is able to exist in multiple forms known as isotopes. Different types of meteorites coming from the asteroids left over in the solar system after planet formation have different proportions of each of these oxygen isotopes. So, by measuring the oxygen isotopes of a given planet, planetary scientists can calculate the different types of asteroid that collided to form the planet. Lunar samples have a very similar oxygen isotope makeup to the Earth. So it's fairly likely based on what we now see in terms of different things that when it got so hot, to go back to an earlier point, when it got so hot from that collision, that these things started mixing together, metals were turned into liquid, and then ultimately as they cooled over time they hardened and they formed back into solids, but still they were mixed together. And so when we take samples from the moon and bring them back here to Earth, they look as though they've been mixed into a giant pot. Some scientists believe that the oxygen isotopes are because the object that hit Earth was made up of the same mixture of meteorites as the Earth itself, potentially suggesting that the impactor planet formed close by in the solar system. Other scientists propose that after the impact, all of the oxygen was able to move around in the hot vapor surrounding the Earth and moon, mixing up all the different oxygen isotopes and erasing any original differences between the Earth and Theia. So maybe there is no difference. However, there are differences between the chemistry of the Earth and moon. At the high temperature reaches during planetary impacts, many elements that we are not used to thinking of as gases, like potassium, zinc, and sodium, can exist as vapor. You heat something up enough, it's going to change. The concentrations of these volatile elements are much lower in lunar rocks than in rocks on Earth. One possibility is that the hot impact debris had a long time to evaporate these elements before it clumped together to form the moon. Another is that when the moon formed, it started off very hot with a deep magma ocean, like the Earth. And the low gravity and lack of atmosphere on the moon allowed volatile elements that wouldn't escape from a large object to evaporate into space. So those potassium, zinc, and sodium. Both of these pieces of evidence are hard to explain without a giant impact. An impact origin for the moon provides the high temperatures needed to explain the lack of potassium, zinc, and sodium on the moon, and also an opportunity for lots of mixing between the proto-Earth and the material that would have become the moon. But when did this impact take place? Good to know. Didn't happen in 1926. Happened many millions of years ago. Scientists believe the moon formed during a giant impact about 60 to 175 million years after the solar system was born. To arrive at this estimate, they can use rocks from Earth. As large planetesimals grow, heat was released by repeated impacts and the radioactive decay elements inside their minerals, enough to cause melting. This allows materials with different densities to separate, with metals like iron and nickel sinking to the inside to form a core and lighter rocks floating on top. And you can see this from an Apollo 15 mission, this lunar rock that was brought back. Very cool. By the time of the moon forming impact, the Earth was already separated into these rock and metal layers. However, The intense force and heat of the impact remelted the proto-Earth, remixing the separate rock and metal. After this mixing, the Earth was still hot enough for separation to occur again and form new rock and metal layers. This is the key to dating when the moon was formed. So, the Earth was still hot enough for separation to occur and form new rock and metal layers. When rock and metal mix, they are able to swap certain elements. Elements like hafnium prefer to be mixed in with rock than with metal. Hafnium decays over about 10 million years to form tungsten. The first time the Earth cooled and separated into rock and metal layers was early in the solar system history. So lots of hafnium was present in the Earth's rocky layer because it hadn't had much time to decay to tungsten yet. Yeah, 10 million years is not a quick afternoon stroll. By the time the moon forming impact occurred, much of this early hafnium had decayed to tungsten. Elements like tungsten preferred to be mixed in with metal, so when the impact remixed the Earth, the newly formed tungsten sank into the metal core. This created a rocky outer layer with a lower concentration of hafnium than before and a metal core with much more tungsten in it. Today, all of the hafnium is gone because it has a short half-life compared to the age of the Earth. However, not all is lost. This makes it very useful for working out the timing of the events in the first 100 million years of the solar system's history. The concentration of tungsten in Earth's rocks depends on when the most recent separation into rock and metal layers occurred. The concentration of tungsten in Earth's rocks is too low to be explained by the metal and rock separating early on, which means something must have remixed the Earth's layer. The best explanation for the heat and energy needed to do this is a giant impact about 60 to 175 million years after the solar system was born. Take a look at this video. This is kind of a similar thing to the previous video that we saw. You can see some differences with this one. Not as much in terms of that massive separation in just right here. I mean, take a look at that, and as that kind of explodes and you can see almost a tail forms out of the Earth, and then compare that to this video right here where there is a brief moment of that, right? When it first makes impact right here, you kind of see that, but immediately on that outer edge, you can see where the moon is eventually going to be formed. And you can see that inside ring area right there is going to go into the Earth, as we will see. Boom, gets sucked into the Earth, and that goes right there. So different than this one. I will trust the other one more so. And then the article continues to talk about what the early Earth and moon looked like. And then finally, let's talk about the questions that remain, because it is not settled science that there was this impact. Like I said, there are multiple different ways to kind of look at the addition of the moon in our solar system. Although scientists agree that the moon formed because of an impact, the details of the impact are still up for debate. Scientists still don't agree on how big the impacting object was, how fast it was traveling, what it was made from, or even whether we should be calling it Theia. I mean, I don't... That last one didn't need to be added. Yeah, it doesn't matter what the name of it is. Some scientists even argue that multiple impacts might have formed the moon instead of just one, which is an interesting thing. If there was, say, 5, 6 different impacts and those came from outside of the solar system, or those came from inside of the solar system, to go back to that point about the protoplanetary disk that surrounded our early sun. Lab experiments help scientists better understand what happens to different rock types and elements under the extreme conditions of large impact events. Professor Nicholas Doufus research group at U Chicago evaporates metals under a vacuum to simulate the conditions present in the cloud of impact debris to try and explain why lunar rocks have so much less elements like sodium, zinc, and potassium compared to the Earth. So maybe we got some. We got some that was delivered to us via a massive rock. Some experiments can be too large for the lab, though, so computer simulations are also used to investigate the moon-forming impact. These simulations enable scientists to virtually smash together the proto-Earth and different types of planetesimals at many speeds and angles to figure out what combinations of properties are more able to form a moon with the size and orbit we see today. In the future, new samples from the moon could give us planetary scientists a wider range of different lunar rock types to work with. This is important because new samples might record different pieces of the moon's history that aren't present in the existing lunar rocks brought back by the Apollo missions. As measurement techniques improve, planetary scientists will also be able to measure new chemical signatures in lunar rocks and improve upon existing measurements. The more measurements scientists have, the more ways they can test different theories about how our moon formed, its relationship to the Earth, and perhaps even how moons might be born around other planets far beyond our solar system. Very, very interesting, right there. And then to kind of top it all off, it did mention something in this last section that I do want to talk about. The more measurements scientists have, the more ways they can test different theories about how our moon formed, its relationship to the Earth, perhaps even how moons might be formed, blah, 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 blah. So obviously with the Artemis mission in full swing, I do think part of the idea with that is to ultimately create a base on the moon. And by doing so, that would allow for these stations ultimately to be made where you can dock in onto the moon and potentially send back either a person from the moon back to Earth or back to the International Space Station, whatever it may be, or to some other craft, to bring back both humans and materials from the moon itself so that we can investigate and see kind of what the moon is made out of. Because if we know the contents of the moon and we know the contents of the Earth, and we see that there are parts from the Earth that are in the moon that are at higher concentrations than we would have thought, then that could rule out something like the moon just came into the orbit of the Earth, did not collide with the Earth at all, and was just a completely foreign body that was independent from the Earth. If we are able to say there are these certain elements that are in both Earth and in moon soil, moon rock, then we can flatly feel more confident in saying that it was a collision between the Earth and the moon.